Hi everyone, myself Konda Krishnudu, Assistant Professor of Physics, Department of Humanities and Science, MLR Institute of Technology, Hyderabad. In the previous session, we discussed about basic information about semiconductors. What are semiconductors? The basic classification of semiconductors into intrinsic and extrinsic. And after that, we discussed origin of energy band formation in solids. And after that, classification of solids into conductors, semiconductors and insulators. So in continuation with that, today we are going to discuss about direct and indirect bandgap semiconductors. Coming to today's review of presentation, today I am going to talk about introduction. Particularly, I am going to explain the basic definition of a bandgap. After that, the two classifications called direct and indirect bandgap semiconductors, and then the difference between direct and indirect bandgap semiconductors, and finally conclusion. Now, coming to the introduction, we know already we discussed what is a semiconductor. Semiconductors are the substances whose current conducting properties lies between that of good conductors and insulators. Whatever may be the property you take, the property of that varies in between that of good conductors and insulators in the case of semiconductors. So there are 11 elements in the periodic table which are having semiconducting properties, and particularly in the case of semiconductors, they are tetravalent in nature. Tetravalent means atoms of semiconductors contains 4 valency electrons in their outermost orbit. Most of the semiconductors contains covalent bond. They are covalent in nature. Means covalent bond is nothing but the bond which is formed due to sharing of valence electrons between the atoms. In the case of semiconductors, this will happen. That's why semiconducting elements will possess covalent bond. And then the most important difference between that of good conductors and semiconductors is, in the case of conductors, the charge carriers are only free electrons. Current conduction takes place only with the help of free electrons in the case of conductors, whereas coming to the case of semiconductors, there exist two types of charge carriers. These two types of charge carriers are nothing but electrons and holes. Next, coming to one more important property of semiconductors, they have negative temperature coefficient of resistance. Negative temperature coefficient of resistance, that is, their resistance varies inversely with the temperature. When we increase temperature of a semiconductor, its resistance decreases. When we decrease the temperature, its resistance increases. That is why they are said to have negative temperature coefficient of resistance. And then, as we discussed, resistivity of them lies between that of good conductors and insulators. Resistivity of semiconductors is more than conductors and less than insulators. Now, coming to the two basic classifications, semiconductors are divided into intrinsic and extrinsic semiconductors. Semiconductors in pure form are called intrinsic semiconductors. So silicon and germanium comes under this category, and most of the cases intrinsic semiconductors have less current conducting properties. To use them in electronic circuits, definitely they should be converted into extrinsic. That is what is called extrinsic semiconductor. Semiconductors in impure form are called extrinsic semiconductors. We will get that by the process called doping. Doping is the process that is required to convert intrinsic semiconductors into extrinsic semiconductors. There are two types of doping mechanisms: adding trivalent or pentavalent impurities. Doping is nothing but the process of adding impurities to pure semiconductors in order to convert them into extrinsic. When we dope intrinsic semiconductors with pentavalent impurities or fifth group elements, then n-type semiconductors can be formed. And when we dope pure semiconductors with trivalent impurities, p-type semiconductors will be formed. So these are the examples of fifth group elements: phosphorus, arsenic, antimony, etc. And gallium, boron, indium, aluminium, all these are the trivalent impurities. Now, in the case of intrinsic semiconductors, there will be equal number of electrons and holes. Here it is written NH is equal to Ne, means number of electrons equal to number of holes in the case of intrinsic semiconductors. Whereas in the case of N-type, Ne is greater than NH. That is, electrons are majority in nature, and whereas in the case of p-type, holes are majority in nature. So this is the basic information about semiconductors and the basic properties of semiconductors. Now coming to the energy gap. So we know in the case of semiconductors there exist two types of bands, valency band and conduction band. Valency band is the lower band and conduction band is the upper band. The energy difference between the two bands is called energy gap, or the distance between the top of the valency band and bottom of the conduction band is called energy gap. So now coming to the main topic of today's session, that is direct and indirect bandgap semiconductors. So this is the picture through which we are going to know, or we are going to discuss about direct and indirect bandgap semiconductors. So using this, using one graph we are going to discuss. That graph is nothing but E versus K, where capital E stands for energy, which we have taken on y-axis, and small k stands for wave vector, which we have taken on x-axis. So the variation of E with respect to K can be able to discuss about the difference between these two, direct and indirect bandgap semiconductors. Now coming to this picture, left side, we are observing that the top of the valency band is this one, and this is the conduction band called upper band, and the bottom of conduction band is this one. So both top of the valency band and the bottom of the conduction band occurs at the same value of K. That is the case of direct bandgap semiconductors. In the case of direct bandgap semiconductors, top of the valency band and the bottom of the conduction band occurs at the same value of K. Whereas in the case of indirect bandgap semiconductors, on the right side diagram, top of the valency band is this one and the bottom of the conduction band is this one. So both are occurring at different values of K. Bottom of the conduction band is occurring at this value of K, and at the top of the valency band occurring at this value of K. So if this is the case, then those semiconductors are called indirect bandgap semiconductors. So that is the basic definition and difference that exists between the two types, direct bandgap and indirect bandgap semiconductors. So now, actually in the previous class we have shown energy band as sharp lines, but in the actual case it will be not like that. So it will be somewhat irregular. So that we are taking into account in order to discuss direct and indirect bandgap semiconductors. Now coming to the basic difference between the direct and indirect bandgap semiconductors. The first one is about the definition, what we discussed just now. Both top of the valency band and the bottom of the conduction band occurs at the same value of K. Then in the case of direct bandgap semiconductors, in the case of indirect bandgap semiconductors, both top of the valency band and bottom of the conduction band occurs at different values of K. Second one, here in the case of direct bandgap semiconductor, direct recombination takes place. Direct recombination. Recombination is nothing but recombination of electrons and holes. What happens when electron and hole recombines? Photon releases. For each combination of electron and hole, one photon releases. So that recombination takes place in the case of directly in the case of direct bandgap semiconductors. Whereas in the case of indirect bandgap semiconductors, that recombination does not take place directly. In the case of direct bandgap semiconductors, because of their direct bandgap, as electrons and holes are going to recombine directly, that difference of energy going to emit in the form of photons. The entire energy of recombination is going to emit in the form of photons in the case of direct bandgap semiconductors, as it is seen here. This is one photon which is releasing as a result of electron and hole recombination directly. Whereas in the case of indirect bandgap semiconductors, along with photons will release. Phonons are nothing but thermal vibrations which will tend to increase the heat of the substance. So in the case of indirect bandgap semiconductors, along with photons, some sort of energy is going to convert into heat because of indirect recombination of electron and holes. How the indirect recombination is taking place, that we can see from this picture. So conduction band is here and it is filled with electrons. Conduction band is here and this is valency band, and electron hole recombination takes place via some intermediate centers. These intermediate centers are called traps. So recombination of electrons and holes takes place via intermediate energy levels. In the case of indirect bandgap semiconductors, those intermediate energy levels are called traps. So because of that, here what happens is, along with photons, phonons will release. That is how recombination takes place in the case of indirect bandgap semiconductors. Now, in the case of direct bandgap semiconductors, the electron hole recombination is considered as radiative recombination. Radiative means the entire energy is going to emit in the form of light. That is what is called radiative recombination. Whereas in the case of indirect bandgap semiconductors, due to indirect recombination, due to recombination via intermediate energy levels, here along with photons, phonons also will release. That is some amount of heat will regulate. So because of this radiative recombination, because of their efficiency in converting electrical energy into light energy, most of the direct bandgap semiconductors are used in optoelectronic devices. There are so many optoelectronic devices. One of them is LED. So in the case, direct bandgap semiconductors are used in constructing LEDs, which is one of the optoelectronic device which is capable of converting electrical energy into light energy. Whereas in the case of indirect bandgap semiconductors, due to indirect recombination, because of their less efficiency, they are not used in optoelectronic devices, whereas they are used in traditional devices like diodes, transistors, etc. So in the construction of diodes and transistors, indirect bandgap semiconductors are used, whereas in the construction of optoelectronic devices like LEDs, direct bandgap semiconductors are used. Finally, coming to the applications, direct bandgap semiconductors example is gallium arsenide. Almost all compound semiconductors are direct bandgap semiconductors. Compound semiconductors are formed simply by adding third group elements with fifth group elements, or even combination of second, sixth group elements also will give rise to direct bandgap semiconductors. Here, if you take the example of direct bandgap semiconductor as gallium arsenide, so gallium is a third group element, whereas arsenic is fifth group element. So like that, combination of third and fifth group elements or second, sixth group element will give rise to direct bandgap semiconductors. Because of their high energy conversion efficiency, they are used in optoelectronic devices, which will convert either light energy into electrical energy or electrical energy into light energy. Whereas in the case of indirect bandgap semiconductors, examples are silicon and germanium. Almost all elemental semiconductors comes under this category, what is called indirect bandgap semiconductors. Example, silicon and germanium, and most of the times these silicon and germaniums are used in making diodes and transistors. Because of their less energy conversion efficiency, they are used in diodes and transistors. Like that, both direct and indirect bandgap semiconductors have their own applications in the field of electronics. So that's all for today's session. In the next class, we are going to discuss about the next topic of the lesson, that is Hall effect and its applications. So Hall effect particularly deals with semiconductor devices, through which we can come to know which type of semiconductor device is given, and after that applications we are going to discuss. Particularly they are used in sensors. Hall effect devices are used in sensors. So that is about the today's session where we discussed about semiconductors introduction, the basic properties, as well as particularly direct and indirect bandgap semiconductors.